Okay, off we go. So here's where we were last time. So we're just getting started in section 6.2. We're going to talk about Green's theorem. I'm building up to it in a way that's establishing what I'm going to call kind of a framework, sort of a strategy that I think is going to apply very effectively to lots of different theorems that we're going to talk about in chapter 6 and 7. So this is going to pay off multiple times, and this is what we're going to see today is just really kind of the first example. So last time we talked about this idea of a quantity on areas. No big deal. All that means is that if you've got some two-dimensional region, right, that I should be able to associate some value to that two-dimensional region. For example, we can talk about the mass in that region, or the area of that region, or the perimeter of that region, whatever. You give me a region, I give you a value. Right? Does that make sense to everybody? It's just something that we associate to every region. And then we talked about an idea that we've actually talked about this a lot previously, this idea of an accumulating quantity. And specifically, I'm saying a quantity that accumulates over areas. And what I mean is that when you take disjoint unions of the areas, like so in the picture, right? We have R1 on the left, R2 on the right, and then we can look at the disjoint union, sort of the whole defined by those two. When you take disjoint unions, that you add the quantity. Right, so mass has this feature, right? The mass of a disjoint union, the whole is the sum of the parts. Likewise with area. The area of a disjoint union, well, the whole is the sum of the parts. Okay, not obvious statements. The reason we have to make a thing out of this is because not every quantity is an accumulating quantity. And so it's not something you can take for granted. It's something you have to appreciate because it isn't always true. And perimeter, I think, is a really nice counterexample. Right? The perimeter of R1 plus the perimeter of R2 is more than the perimeter of the union. Does everybody see that? Any questions about that? So, okay, so not everything is an accumulating quantity. And so when something is an accumulating quantity, we have a useful feature that we're going to be able to take advantage of. Okay, that's about where we left off last time. So, here's the first thing I'm going to do with an accumulating quantity. This is a little bit weird seeming. This is not something you have to do, but I think this is extremely helpful, and I strongly encourage everyone to think this way. Y'all okay back there? Okay. When you have an accumulating quantity, you can think of it as being kind of like a substance. I know that's weird. Right? It's a very strange way to think, but you don't have to, but you can think of an accumulating quantity as being a substance. Now, what an outrageous suggestion, and a nice example of this seeming very unnatural is let's think about work. Right? So looking at this region right here, I like to think of this as the bottom of a swimming pool, like a backyard swimming pool kind of a thing. And maybe somebody drained the pool, and we got to get down on our hands and knees with a toothbrush, and we got to clean all the whatever mold or mildew or whatever off the bottom of the pool. This is going to be a lot of work, right? And I think it's fair to say that this is an accumulating quantity. The amount of work it would take me to scrub that piece, plus the amount of work it would take me to scrub the next piece, plus, add up the amount of work for each piece, that'll give me the total amount of work it would take me to do the whole, right? So the whole is the sum of the parts. But does that mean work is a stuff? Is work a substance? And it certainly doesn't feel like it is. And in fact, physically, of course, it's not, right? Work is not a substance. It's not a physical thing. It's not a concrete type of a stuff. But you can pretend that it is. Right? Now, what would be the consequences of imagining something that isn't actually true if I were to imagine work as being a kind of a substance? Well, I would be thinking about, then there's a certain amount of that substance in that little region, and there's a certain amount of that substance in that little region, and there's a certain amount of that substance in that little region, and we would go look at all the regions, and I would argue that the total amount of the substance is the sum of the amounts of the substance in each little part. In other words, I would declare the whole to be the sum of the parts, which it is. Right? So nothing bad happens. Right? The way that thinking of an accumulating quantity as being a substance, even if it's not, right? It's just another way to think of how we would do exactly the same calculation, namely the whole is the sum of the parts. Now, just by way of counterexample, you cannot think of perimeter as being a substance. Right? This would be a real problem. If you tried to think of perimeter as a quantity as being a substance, well then the amount of the substance there, the amount of the substance there, the amount of the substance there, I'd be looking at the perimeters of all of these individual regions and adding those up, and I would get the wrong answer. Right? Because perimeter is not an accumulating quantity. It does not behave like a substance. But anything that's an accumulating quantity does. So it's just a point of view, and again, you don't have to think about it that way, but there's some really nice benefits of thinking about it that way. I'm going to push that we're going to think of accumulating quantities as substances, even though they aren't, and we're going to reap some nice benefits. Okay, related note. When you have an accumulating quantity, which of course we are now thinking of as a kind of stuff, then we can talk about the associated densities. Now, mass density, easy concept, right? We talked about mass density many times. Y'all were aware of mass density before you started this class. Mass is an accumulating quantity. We can look at how much mass there is on any given little region. We can divide by the area of that region. We can take limits as we get smaller and smaller. This is how you define good old-fashioned density, right? What I'm going to call mass density, because mass is the accumulating quantity for which this is the corresponding density. Population density. Again, now population is an accumulating quantity. The whole is the sum of the parts. And we can talk about population per unit area. Same thing, right? Little bit different because we don't think of population as being a substance, but we're physical, right? I'm physical. We're kind of a substance of sorts, right? It's not super weird. Where it's going to start to seem weird is when I talk about work density. Because work is not a substance, right? But we're thinking of it as a substance because accumulating quantities we can think of as a substance. And if we think about it as a substance, we can talk about work to scrub the bottom of the pool, work per unit area of the pool that I'm scrubbing. So, kind of a density of sorts. What do you think? Am I willing to play along with this point of view? All right. And of course, densities have this nice feature that they're what you multiply by size to get stuff. And again, the stuff being the accumulating quantities in question. All right. Well, hey, once you've got a density, then you can start writing down integrals. And now, again, here's my arguably my favorite example of what to compute with an integral. Favorite sort of starter example, first example. We've computed mass, right? We've done this in many different contexts. We've done it on intervals. We've done it on two-dimensional regions. We've done it on volumes. And the big idea is that the whole is the sum of the parts, and each part is density times size. Right? Physically relatable, no big deal. Double integral you can compute by whatever means you like. And now I'm just going to say, well, you know what? You can do that with any accumulating quantity. For example, work. Again, we don't think of that as being a stuff. But look, the whole is the sum of the parts. Right? Work, per the example that we gave with the bottom of the pool and the toothbrush, the whole is the sum of the parts. And on any given piece, right, we've got this brand new idea of work density. And that work density tells me how to compute work as density times area. And so even though it's not a substance, I'm going to compute work by an argument that's morally, structurally identical to the process by which I compute mass. I'm treating it like it's a stuff even though it's not physically a stuff. Okay, so we're going to do several examples of this kind of thing as we move along through the material. Our first example is coming up in just moments. And by the way, just a little terminology. Theorems that we get by making this argument. Sometimes I call these accumulation theorems because accumulation is the foot in the door. That's what makes it possible. That's why I can write it down as an integral in the first place. So it's just a terminology that I like. You might not hear that elsewhere. I also sometimes call these density theorems because in both cases, in all such cases, the corresponding density is the integrand for the resulting integral. So another terminology that, again, I like. You may or may not see these elsewhere. Okay, and then last comment. Everything I did here, I did in terms of double integrals over areas, just so that I could have an example to kind of, draw pictures of. And our first example will be two-dimensional, appropriate to this. But you can also talk about accumulation over lengths. You can talk about accumulations over volumes. And analogously, for example, let's look at over volumes. This is how you would compute an accumulating quantity over volumes. And again, the whole is the sum of the parts. Now the parts are kind of in three different directions instead of two, but still whole is the sum of the parts. And each part is a density times the size. So same basic ideas, just different geometry. Okay. All right, so that's a big picture strategy. I know it seems pretty abstract, but lots of payout on lots of big theorems, and we're going to see those over the next few weeks here. Okay, so to get to our first big example in R2, two dimensions, I do have to define a technical point. This is very, very important. It is, however, unfortunately, kind of boring. But we have to worry about a detail about the word boundary. Now, I think y'all are probably previously familiar with the word boundary. It's, I like to think of it as the border between where your set is and where your set isn't. Right? That's what a boundary is. It's where the fence is that keeps the sheep in. Right? There's where the sheep are, and then there's where the sheep aren't. Does that make sense? Everybody familiar with this term, boundary? Okay. So, here's what we're going to do with it. Henceforth, we're going to think about boundaries as being oriented. So y'all will recall, we talked about oriented curves, right? When you do a vector line integral, your domain, you got to tell me which direction we're going. If we're computing work, I need to know, you want to know how much work it takes to go up the mountain road to the top of the mountain or down the mountain road to the bottom of the mountain. Right? So direction matters. Henceforth, the word boundary will always refer to something that is oriented. And furthermore, something that is oriented according to a very specific convention. Here's the convention. If you have some region, and for whatever reason I like to think of this as being like a grassy field. So some two-dimensional region. We can talk about the boundary. Maybe there's a little walking path going along the boundary there. That's the boundary of our grassy field. The orientation. What we mean when we say the word boundary. Boundary means oriented. In this case, this direction, specifically that direction, as described by this criterion. You go whichever direction puts the grassy field on your left. It's arbitrary. Somebody made that up. I'm going to say no particularly good reason. There was probably a decent reason, but it's nothing we need to worry about. It is ultimately arbitrary. Long ago, they could have decided on the right. there'd be minus signs, everything would be different, but ultimately it would work just fine. But that's not the convention. The convention is, and we're going to stick with what planet Earth does, the convention is on the left. So notice, as I walk along this walking path, right, enjoying the view to my left, a nice grassy field, as I go in the direction indicated by this correct orientation, notice the field is on my left. That make sense to everybody? It's just a convention. Now, if I were on the other side of the field, if I were up on the north side of the field, I would have to go that way along the boundary. Again, here's a boundary curve. I would have to go that way so that as I walk along the boundary, the region is on my left. Right? So you can't oversimplify this. It's not like, we always go to the right, or we always go to the left, or we always go up, or we always go down. No, you can't. It's not that simple. You always go whichever direction puts the thing you're talking about the boundary of on your left as you go in that direction. Now, what a lot of people try to do, and this is not terribly far off, but it's ultimately not quite true, is say, okay, well, here's the whole field, and check it out, we're always going counterclockwise. I'm going to put a question mark on that. Certainly for the picture I have on the left here, no matter where I am, as I walk counterclockwise around this boundary curve, the field is always on my left. Seems like it's working nicely. The problem is that not everything is that shape. And in particular, let's look at a grassy field that looks like this, that maybe has a couple of ponds in the middle of it. Right? Part of the boundary is around the outside like this. Part of the boundary, though, is the edge of the pond. Maybe the edge of the other pond also. And, well, the thing is, at a point like that, in order to walk such that the field is on my left, I have to go that way. I have to go this way as indicated here. The field is on my left, and notice I'm not going counterclockwise. I'm going clockwise. Everybody see my example there? So, dangerous. Let's see here. I'm going to put this in red. It's halfway true. If you're going around the outside part of the boundary, yeah, it's counterclockwise. If you're going around the outside part of the boundary, which you might not be. Okay. All right. Okay, so with all that set up, now we have a convention for what we mean by boundary. Recall, this was all just kind of some setup. What we're really doing is we're talking about how we're going to use accumulating quantities. We're going to think of them as being kind of like a substance, even if they aren't. We're going to associate a corresponding notion of density, and then we're going to declare that we can compute it with an integral. We're going to do this with any accumulating quantity we can find, and here's the accumulating quantity that I want to talk about now. It's very surprising. It's counterintuitive. Boundary circulation. This is an accumulating quantity. And let me remind you what these words mean. Boundary, we just got through talking about. Orientation is very important. When we say boundary, again, part of your job, right, is to remember that when you see that word boundary, that means oriented according to a very specific convention, and you have to follow that convention. That's what boundary means. Circulation, recall, means vector line integral on a closed curve. Conveniently, boundaries are always closed curves. So boundary circulation means whatever region you give me, right? If you give me some region like this, some big grassy field like so, Boundary circulation says, okay, I'm going to look at the boundary. I'm going to follow the conventions about orientation. And then I'm going to compute the circulation around that boundary, circulation of whatever, some given vector field, let's call it F. So you give me a vector field, boundary circulation is defined like so, and I claim it is an accumulated quantity. Now it doesn't look like it. In fact, it looks like it isn't. Let me first try to persuade you on the tempting claim, the tempting suggestion that boundary circulation is not an accumulating quantity. And tell me if this isn't tempting. Well, wait a minute. If I look at the whole, boundary circulation is a line integral like so. If I look at the left, then boundary circulation is like that. I'm already kind of thinking, like, there's no way this is going to work out. The boundary circulation around the whole doesn't include this piece right here that's clearly going to show up by virtue of it being part of the boundary circulation of the left. So I've already got a discrepancy. I've already got a problem, right? Okay, but we'll play the game. We'll keep going. We'll look also at the right. And on the right, boundary circulation would go like so. Now I've just got more problem, arguably. Again, this kind of shared edge in the middle is, again, there's no purple where this green and blue are. Right? Now, again, keep in mind the goal is we're trying to argue. If I were to claim that this is an accumulation, I would need the left boundary circulation plus the right boundary circulation to equal to the overall disjoint union boundary circulation. I need green plus blue to be purple. Is green plus blue equal to purple? And we've got this problem in the middle. Now, along in here, the green tracks the purple perfectly. Along in here, the blue tracks the purple perfectly. And I'm going to say I'm going to cancel all of the stuff that tracks perfectly because that's canceling the same from both sides of the equation. And here we have our discrepancy. Our discrepancy, the problem, the thing that's making our equation not seem to work out is that on this shared edge in the middle, I've got green and blue but no purple. There's our problem. And here's why that problem is not a problem. That's two line integrals on the same curve, but with opposite orientations. They're exact negatives of each other, and they cancel. And it's this discrepancy, this problem, is exactly zero. Everybody see what happened there? It's kind of unexpected. I mean, it looks like we've identified a problem. It looks like we've identified a way in which this formula is not going to work. We've got a plus frowny face right there to make this equation work, but we've now realized the frowny face is zero. What do you think? All right, well, this is why it works. Very counterintuitive, but boundary circulation is an accumulating quantity. And at this point, we are in good shape. Let's see if I can get this to cooperate. Yeah, there we go. Remember, here's our sort of strategy. Our strategy is, once you identify an accumulating quantity, declare that it behaves like a substance, talk about the associated density. We'll have to do a computation to get that. Once you have an associated density, you can compute it with an integral, and you've got yourself a theorem. And we've done this several times before. Mass, accumulating quantity holds the sum of the parts, integral of mass density. Work, blah, 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 integral of work density. And we're just going to do the same thing now with our new accumulating quantity, boundary circulation, we're going to view as being a substance, even though it isn't. We're going to write down an associated density, and we're going to compute it with an integral, just like we've done before. Now, the actual computation of the corresponding density, keep in mind, I guess that's fine. Keep in mind boundary circulation. This is our accumulating quantity. So I'm going to call the density circulation density. We could call it boundary circulation density, but the boundary is implied. So circulation density, here's the formula. dq dx minus dp dy. Keep in mind, when we say circulation density, that means we're computing boundary circulations for a given vector field F. Whatever this vector field might be, I'm going to say P comma Q, and compute this little magic expression right here, dq dx minus dp dy. That, as it turns out, is the circulation density. Exactly why that works is, I'm going to say not worth the time investment it would take to do that calculation. It's details. They're important details, to be fair, right? But it is just details, and time's precious. And ultimately, I don't think the intuition that you would get from that calculation is worth the time and effort that it would take in class. So I prefer to focus on more sort of intuitive kind of stuff. So anyway, that we're just going to take this as a given. As for terminology, the most common notation terminology is to call this curl. Y'all remember curl from chapter 3? It was a long time ago. And at the time, you may recall, I was very kind of apologetic. We don't have the tools to make sense out of this. I'm claiming that curl represents how the fluid is sort of rotating, right? You drop a leaf into the fluid and the leaf it might go somewhere, but it also would be rotating, and that how that leaf rotates is what curl computes for you. I said, well, someday we'll have the tools to be able to make sense out of that. Here we are. Why is it that curl computes how those little leaves rotate? Because curl, this expression, is circulation density. And circulation, you'll recall, circulation says we're looking at the vector line integral around a boundary, right? And vector line integrals represent the extent to which the fluid is going along with that closed curve, that boundary, and of course closed curves go around in kind of sort of circles. That make sense? So that's the point. This is why curl, it represents how the fluid is rotating, because it comes straight out of circulation. It is directly related to circulation. In the same way that mass density is a way of keeping track of mass and how much of the mass is where, likewise curl is a way of keeping track of where is circulation and how much of the circulation is where. Thinking of circulation again as being a kind of a substance. How are we doing? You all okay? Willing to believe it? Okay. All right, some other notations. Rote looks like rot, which I think is why this is not a more popular notation. But this is an abbreviation of the word rotation. And frankly, I think that's a better metaphor. After all, that is how we think about curl. Curl is telling us you drop a leaf into the surface of this little river, and the curl is telling you how that leaf is literally going to be rotating around. Right? So I think this is really the better term. Curl kind of suggests, what is curl? Outside of a math context, it kind of suggests something is bent, but it doesn't have the element of motion that rotation captures, which I think is really more relevant. So anyway, I like the term rote, but I don't use it because it's much less common. Curl is the much more common term. Here's a weird callback. Y'all may recall this thing here. The wedge product. Y'all remember that from chapter 1? It was a long time ago. We talked about cross product. Specifically, cross product is a peculiarity of 3 dimensions. Cross product as a operation between 2 vectors only for 3 dimensions. The wedge product is sort of a 2-dimensional. It's not an analog exactly, but it's kind of similar. And if you take the del operator and a vector field P comma Q, and you take the wedge product, son of a gun, you will in fact get curl. So this is an alternative notation. It's not super common, but it is pretty compact. And you may recall we have different notations for, like, divergence is del dot, and 3-dimensional curl we talked about long ago is del cross. So this fits into that pattern. Del wedge is kind of elegant in that way. So some people like that. Be aware, heads up, keep your eyes open for it. Years ago, I liked the term Green's operator. We're about to write down Green's theorem. The operator in Green's theorem is this thing. So I liked the term Green's operator, and with that in mind, I started using this notation GRN to suggest Green's operator. You won't probably see that anywhere except for my old tests, which if you go through for your practice purposes, of course you're going to see a lot of. So anyway, on my old tests, when you see GRN, it just means curl. And I would encourage you just to scratch that out and just write curl. That's what we're going to be using. Yeah.
So for like our exams, we would see curl.
I have no intentions of resuming the use of GRN. Okay. Correct. Cool. Anybody else while we're at it? Okay. I really discourage this one. I mean, I don't want to X through it, but I am going to put a frowny face next to it. It's got a problem. This notation, you may have already noticed, our vector field is 2-dimensional. There is no cross product for a 2-dimensional thing. It does not make sense. Colley uses this notation. It's my least favorite thing in Colley's book, honestly. But the reason is that if you were to take P comma Q, and if you were to reinterpret that as P comma Q comma 0, if you were to kind of force it to be a 3-dimensional thing, even though it's not, and if you were to compute the curl of that, and then take a dot product with 0, 0, 1, y'all may remember, IJK, right? This is that third standard basis vector. In fact, you would get this. So it kind of works in a way, but I ask, why? What's the benefit? What's the situation where this notation is more helpful to me than any of these others? It's got more pen strokes. It requires me to be sloppy about what I mean by F. I interpret it as being 2-dimensional or 3-dimensional depending on the context. That's not cool. I think it's got a lot of downsides, and I don't really see the upsides. Yes?
Would it be more helpful if you had something that's a 3-dimensional vector field?
If you have 100%. If you have a 3-dimensional, kind of. So when we get to, we are eventually going to talk about a 3-dimensional version of this. In that 3-dimensional version, there will be, I don't want to get too far ahead of myself here, there will be a notion of boundary circulation. There will be an associated density. The problem is that density will then be a vector quantity, not a scalar. But the vector quantity that it is very effectively written as del cross F. Absolutely. But there's no dot K. So kind of in a 3-dimensional context, and I'm sure that's her motivation, right? The reason, because this is suggestive of del cross F. I just don't think that is worth the ugliness of deliberately misinterpreting what F is. To me, that's a pretty big negative for me personally. Is that satisfying? Yeah. Okay. So we're in business. We're ready to do this thing. Let me remind you, the big strategy, accumulating quantity. View it as a stuff. interpreted as having a corresponding density. And stuff, the whole is the sum of the parts, and it's an integral of the density. And that's what we're going to do here. That's exactly what I have here. We have ourselves a quantity called circulation, boundary circulation. We have argued that it's an accumulating quantity, so the whole is the sum of the parts. And you can compute, let me be careful here. You can compute on any given little piece, any little part, stuff is density times size. It's just like computing any other kind of a substance. The whole is the sum of the parts, and any part is density times size. It's this all over again. Just a different kind of a substance. Okay, now, so what? It's cute, I suppose, but why do we care? Notice the punchline. You know, we were thinking of circulation as being a kind of a stuff, but it's also an integral. Right? It's a vector line integral over a boundary curve. And what this ultimately theorem is telling us is that I can compute this integral if I want to. I could, if I were so inclined, I can compute this vector line integral with a double integral. And that's super surprising. It's very unexpected. Right? They're totally different domains, right? This double integral is over the interior of our region. This line integral is over the boundary of our region. Different domains. They'll always give you the same answer. Very unexpected. And the way we're going to use this, most of the time, a few counterexamples, most of the time, we're going to find ourselves looking at a vector line integral, not knowing how to compute it, or not being able to compute it without getting into some really nasty integrals, some really ugly business. And in the hopes of avoiding all of that ugliness, we say, hey, I wonder if maybe I can compute this double integral instead. And sometimes, surprisingly often, in fact, this is a really easy integral. So this is a computational tool for vector line integrals, boundary vector line integrals, boundary circulations. Okay. All right. Let's do one. We've already talked through this right here. Example. We are going to compute this vector line integral right here. Got a vector field given. We got a curve given. Notice our curve. Our curve is the clockwise oriented unit circle, like so. Again, we got a vector field. We want to compute this vector line integral. I suppose we could brute force this. Right? I mean, before today, we had really only one method for computing vector line integrals. The way you compute a vector line integral is you parameterize your curve, your oriented curve. We need to parameterize the unit circle. That's going to make x and y sines and cosines, which I'm then going to have to plug into my vector field, which already had a tangent in it. I was already kind of unhappy about that, right? But now it's got tangent of y. Y is going to be either sine or cosine or something like that. Now I'm looking at tangent of like cosine of t. That's super weird to have inside of an integral. I'm concerned this is going to be a hard integral. Right? Doesn't that look like a hard one? I think this will be a hard one. Certainly has potential to be a hard one. Okay, let's see if we can come up with a better way. We, after all, have a brand new theorem that helps us compute line integrals. Check it out. There's a line integral. There is a very important asterisk on this. Notice it says right here, This theorem does not apply to just any old vector line integral. Not just kind of a whatever random line integral. Very explicitly, it's only for line integrals on boundaries. It's got to be a boundary. That's important to why the theorem works. Right? That cancellation that we saw on the interior shared edge is because of the orientation conventions on boundaries. So if we want to use this theorem, if I want to compute a line integral with a double integral, I've got to make sure that my domain curve is a boundary. Is this domain curve, this green domain curve, is that a boundary? Close, but not quite. It's going the wrong way. Right? We have these important rules about orientation, boundary orientations. If I was going to declare this to be a boundary, the boundary of the region D has to go the other way. This green curve, C, does not go the correct direction. The region's not on my left. The region's on my right. Everybody see the problem? Feel free to ask a question if you got a question. Okay, so, right. Okay, well, here's the good news. That curve and this curve, same underlying curve, just oriented in opposite directions. And that curve, the blue curve, literally a boundary. Details and all. Orientation, correct. That curve C minus, that blue curve C minus is a boundary. It's the boundary of that gray region D. Is that cool? Everybody with me? Does that make sense? So we've got a foot in the door. Now, in order to be able to do this, we do have to recognize that minus sign. So again, we start with an integral over the curve C. Very first thing we do is we say, okay, let's orient the other direction, which we fix with this minus sign. That's how opposite orientations work. And then I say, hey, that curve C minus, that curve is a boundary. And once you recognize that that's a boundary, then we can invoke Green's theorem. Green's theorem says that boundary line integrals are double integral over the interior of the curve. And now we've transformed the question, how easy is this double integral going to be? Well, we'll get to that in a second. It turns out really nice. But before we move on, does everybody see how I negotiated my way into having a curve that's a boundary and then invoked Green's theorem? Everybody happy with that? Okay. All right. And of course the minus sign comes along for the ride, right? Okay, so now let's look at our new integral that we have to entertain, and we've got to have to compute this curl. We've got a formula for curl, dq dx minus dp dy, right? And remember, that's p and that's q. So dq dx minus dp dy, we're going to take this vector field f. And, well, whoops. We get this calculation here because dq dx is 3. dp dy is 1. So 3 minus 1. Super easy. Now we've got to be fair, it's a double integral, right? And there is a legitimate concern, hey, with a double integral, am I going to have to slice this up and think about iterated bounds and stuff like that? But in this case, the integrand is a constant. You factor out the 2. Now I'm just literally computing the area of that domain. The area is the area of a unit disk, which is pi. Right? So it's a geometrically convenient integral. And so, done. What do you think? Everybody all right with that? this kind of sneaks up on us, doesn't it? Right? So we started off with this abstract discussion about accumulating quantities, and you can think of it as a stuff, and that you can argue, at least imagine, an associated density, and then we found a weird accumulating quantity, and all of a sudden we're computing one kind of integral with a different kind of integral. I think it sneaks up on us quite a bit. And by the way, that's going to happen with the several remaining big theorems that we're going to see with this same strategy. This same strategy here, where we identify accumulating quantities, think of them as a stuff, talk about the associated density, and then compute with integrals. We're going to see this for Gauss's divergence theorem, which allows you to compute one kind of integral with a different kind of integral. We're going to see this with Stokes's curl theorem, which allows you to compute one kind of integral with a different kind of integral. Just like Green's theorem, which, as we see here, we compute one kind of integral with a different kind of integral. All right, we'll do one more example and then call it a day. This is just kind of geometrically different. Our curve for our line integral is 4 line segments that make up what I like to call sort of a triangular figure 8, if you will. Now, how would we compute this? Again, sort of the old-fashioned way, the blunt, brute force way to do this. I would have to parameterize all 4 of these line segments. Not that that's hard, but I would have to do 4 parameterizations. I would have to do 4 pullbacks. I would have to do 4 separate corresponding single variable integrals, and it's not that we can't do it, but it's a lot of tedium. Okay. So here's the big idea. Break up these longer edges, like so, into pairs of shorter edges. Now that's the same, ultimately the same, we're covering all the same turf, right? Just in 2 separate chunks. And when you do that, notice I can sort of break it up into 2 separate pieces. I've got a loop around D1 and I've got a loop around D2. Now, why would I want to do such a thing? Well, conveniently what I have in green there is literally the boundary of D1. And what I have still remaining in blue, it goes around D2. I was going to say that it's the boundary of D2, but I can't call it the boundary of D2 because boundary is a loaded word. Boundary means oriented according to very strict, rigid conventions, and this is going the wrong way. So, we fix it by just recognizing that it's going the wrong way. We fix it with a minus sign. So let's pause on this for a second. Is everybody on board? Everybody see what we're doing here? Yeah, cool. All right. So the integral on that curve C is the sum of these. You got to account for the orientations, right? You got to throw in the appropriate minus sign. But basically, we're talking about line integral around the boundary of D1 and a line integral around the boundary of D2. Just appropriately fixed with minus signs. Okay. Great, we have a couple of boundaries. Anytime you're looking at a boundary line integral, you can invoke Green's theorem. We've got 2 different regions, 2 different boundaries, 2 different instances of Green's theorem. We're going to have to compute the curl, it would seem. Let's see here. How do we compute the curl? Well, again, dq dx minus dp dy. A little micro calculus, a little bit of arithmetic. Curl is 9. Double check me on that. Make sure that I'm right, but also make sure that you can do that. Curl is 9. Thankfully, very nice. We have a couple of constants. Well, I guess you call it a single constant, but two different integrals where the integrand is a constant. The integrand factors out. Again, you're left with just computing the areas. And then you notice that our two areas, come on, there we go. My two areas are clearly the same area. Those two triangles are the exact same size. So these two things are the same. Difference is 0. We're done. We walk away. Didn't have to parameterize anything. Everybody happy? We'll call it a day here. Y'all have a good one. See you later.